that if I am uniform when fixing the amount of vertices, then I am a Q-Boltzmann. Now when we want to show that the root invariance plus Markov property implies that I have to be uniform when I fix the vertices. Okay? So this goes by induction. So we'll do 3 implies 2. Okay, maybe I can do a little bit better my resume. So essentially what we are trying to do, of course, is to try to generalize this Markov property in the case of maps, instead of just functions from a graph to a graph to a group. So to do that, we somehow realized that Boltzmann map were the only natural one, a natural class of maps that satisfy the Markov property. And now what we want to show is that they are the only reasonable one, and reasonable one means that they are the only ones that have the Markov property and are invariant under rerouting. I think that's the most reasonable way of thinking about it. And what we show is that if we were uniform given the amount of vertices I have, then I have n plus Markov property, which is 2 plus Markov property. This implies that I was a Q-Boltzmann. And now what we want to show is that if we were reroute invariant, then we have to be uniform when fixing the amount of vertices. And the way to do that is that we are going to work by induction on the amount of vertices. So we start with 0 vertices. So 0 vertices is everyone gets connected with everyone. So you have here two L edges. So you have this vertex, you have 2 L edges. And I have 0 vertices, so means everyone is connected with everyone. Okay? So what we are going to do is, let's compute the probability of Q is equal to that. Okay, I don't like this event. Why? Because this edge is not connected with a neighbor. So I will change the root. Sorry, the root edge is not connected with a neighbor. So let's change the root edge. So I will change to this root edge. So this one is connected to that one, let's say. I have a lot of it. Okay, so I change this one to that one, root edge. So this will be equal to the probability L of a type 2 0 L minus 1 times the probability of L minus 1 that Q is equal to something. Yes? So I just realized that I could glue these two together and I got something else. So now I can just use induction to see that for if I have 0 faces, all of them can be written as probability of L of type 2. So it's a product over K running from 1 up to L. So here I have L minus K, type L minus K, 0, L minus K minus 1, or something like that. Okay? So all of them have the same law. All of them are essentially this probability. So we know that when I have 0 vertices, we are uniform on cardinal of B equal to 0. Now we have to show the same thing for every L. So this is important. For every L. So I'm not true for every L, we have uniform choice. Okay? So now let us cardinal of B equal to something. Okay? So then that means that so let me take something. So we have here have the root h. Maybe the root h is connected to this. Okay, so something like this. I don't like this thing. I don't like this thing because the root h is connected to itself through the. The root h finishes and begins in the same vertex. So now I can change my root edge. I can always change my root edge to someone that has a vertex, because I have vertex equal to k. At least one other vertex is connected to the root. If not, I have 0 internal vertices. So this is equal to the probability of L of Q equal to, let's say, whatever, and something connected to a vertex. So it is the same, I just did a rerouting. So this is connected to a vertex, which is doing something like that. So this is equal to the probability of N of having something of type 1 times the probability of L plus 1 of my Q equal to something specific. Yes. So I'm just doing one pitting. Okay, but this is true for every map I take. Okay, and this one does not depend. So this one has the amount of bases the amount of vertices this has is equal to k minus 1 now. Because after a type 2 I discover a new vertex, so now I have something to be discovered that has k minus 1 vertices. But everything with k minus 1 vertex was uniform. So this one does not depend on the drawing I have here. Yes? So every object with k plus 1 can be written as probability of getting a type 1 times something constant, so all of them are constant. So all of them are uniform. So this implies uniformity. Oh. So that's what I wanted to tell about undecorated maps. Okay? So the only reasonable undecorated map, the only probability measure on undecorated maps that do not have that are invariant under rerouting are the Boltzmann maps. So that's a reason to study Boltzmann map. People have studied quite a lot. If you have ever seen a talk in planar maps, either it is about Boltzmann map or about uniformly chosen ones, which is essentially just a condition, a Boltzmann condition on the amount of vertices. However, what really is interesting in statistical physics is not only working with uniformly chosen maps, but taking a map proportional to certain objects. So one does not want to take maps which are uniformly chosen, but that take different laws. And in particular, we are interested when we have a spin system. So let me introduce spin decorated maps. So a spin decorated map is now going to be a pair of two things. So one is the map, and the other one is going to be a decoration. Okay, so let me first draw the map. So let me say my map is this one. Okay, so this is my map. Okay, I will add now a boundary condition. I want phi will be a function that goes from my map to, let me put R, but it could be RD. Okay, so it will go from the vertices of my map to RD, and only the internal vertices, so only this one. Okay, and I will add a boundary condition here. So what's a boundary condition? I will add to, so this is my root edge, I will put it here. To each of these points, I will assign a value that's going to be deterministic. So this is B0, B1, until B to L minus 1. Okay, so they come in And they are going to be the boundary condition of my statistical physics model. Yes. So this were phi, and what is the probability? What is the probability density of phi given that I know the map? So imagine that someone already gives you the map. How do you sample the decoration? The decoration will be a generalized Ising model, okay, with the same mu for every vertex. So this will be proportional to the product of the vertices of a certain measure psi of v times the product of the edges of the exponential of minus beta divided by 2. Okay, so I will add, okay, let me write it like that, of sum of psi I minus psi j square. Yes. So essentially you have the energy of an Ising or a Gaussian free field. So this one we will write as exponential of the energy minus the energy of psi. Okay. So the beta I'm going to eat it in the energy, just not to write it all the time. So given that I know the geometry, then the decoration is just a generalized sigma. So the decoration has the Markov property. And what we are interested in is in which of these measures, which measure I can put, okay, sorry, I forgot. So this ij also count these edges. And in these edges I am putting boundary conditions. So I have boundary condition v0, so this is psi v. So here I get, for this edge, I get exponential of minus beta divided by 2 psi v minus v0 squared. Okay? So that's why I need to put boundary conditions. So now I have something that depends on two things. So this depends on b. This depends on the boundary condition. For each boundary condition, I will have a different law. Okay, so then, as again, what would be the Markov property? In this setup, one would want to take Q and psi, a random spin decorated map, okay, so for a spin decorated map is something like this. This comes, mu is given. So if someone tells you that you have a spin decorated map, they already told you the mu. So they can tell you this is an Ising decorated map. Mu is delta minus 1, delta Dirac in minus 1, Dirac in plus 1. Someone can tell you you have a GFF decorated map, in which case mu is a Lebesgue measure. Okay? So this you are allowed. People are giving you explicitly what the spin decorated map, what the mu is. Then conditionally, on, well, that M is containing Q as before, and the restriction of phi to the vertices of M. We can write, of course, we can write Q as M glued with something, QH. H where if you look at QH and phi restricted to QH, these are independent, they are independent spin decorated maps. I'm going to put here random. Spin decorated map with boundary condition, because now spin decorated maps come with a boundary condition, and the boundary condition induced by what I am seeing in M, by phi restricted to the whole. Yes. So meaning that if, okay, happens because I didn't do a good drawing, but let's say that we discover this. Let's say that we have already discovered, so I always discover these edges, but furthermore I discover this up to here. Now the boundary condition is psi b here, psi b here, psi b here. Yes? Or phi, whatever. So psi b, b1, b2, b3, b4, b5. So now, of course, they come with a change of the boundary conditions because they are together. So the question is to describe which probability measures have the which probability measure have the Markov property for spin decorated maps. And the answer, as before, are going to be Boltzmann decorated maps. So what's
Is it important now that it's a generalized GFF? Because in principle you could do this for hardcore models.
Yeah, I could do this for some energies according to edges. Yes, it will not for this be absolutely important, but it's somehow good to fix ideas. Because afterwards we want to extend them to the metric graph. And for the metric graph, it is nicer. So we want to use essentially the same techniques. So what is the? So now note that. So we need to look for probability measures indexed not by one thing but by two things. So they should be indexed by the length of the boundary. But by the decoration in the boundary, by the boundary condition. So now it's really a much bigger family of measures. So Boltzmann maps. So Q psi is a Boltzmann map. If the probability, so here is going to be a density or a probability according to our measure mu, because our measure mu could be continuous or discrete. We are always going to think it's going to be discrete, even though the interesting case is when it is continuous. Q in m comma psi, let's say. So this is going to be proportional to what? It's going to be Q to the amount of vertices times the energy. So times V on the vertices of M of mu psi V times exponential of the energy minus beta. The energy that, of course, the energy depends on the graph you are working and on the equation. I said that I'm not going to put. So okay, so you are choosing something proportional to the decoration. So let's note some properties. Before, so I'm probably not going to show the Markov property, but let me say that this is respects the chief. So it's not shift invariant in the following sense that it's not shift invariant because, sorry, PLB. So this depends on the length and the decoration. So for each decoration you have a different, for each boundary condition you have a different probability measure because it has to do with how it is interacting with the object. Okay? So if one shifts the object, you don't have the same probability because now your energy is not the same. If you chip the object, your energy, you change the boundary values of your object. If you do a chip, now B0 is not at the same point. So you have to, after doing a chip, you have the same probability as long as you chip the boundary condition. Also, chip the boundary condition. So you have to chip not only you don't only have to change the edge, but somehow in the notation you have to also put B0 where B0 will be and everything. But essentially this is just because it's only seeing the energy, so you just have to keep the energy. You have to do any change in which you keep the amount of vertices and the energy, then you are essentially the same likelihood to appear. Okay? So another thing, so it is Q is Boltzmann distributed. So Q, what do I mean by this? I mean that the law of Q, when fixing the amount of vertices. So if I fix the amount of vertices, I'm Boltzmann distributed, and by this I mean that the probability LB of Q equal M over the probability LB of Q equal M tilde, when M and M tilde have the same amount of vertices, this will be equal to the partition function of the sum or the integral over this is M psi B exponential of the energy exponential minus the energy psi tilde the vertices mu psi tilde B exponential of minus the energy tilde psi tilde. So this is the partition function of the function depending on M, and this depends on M and on the boundary condition. So the partition function depends on your boundary condition and on your graph you are working with. So this will be the ratio of partition functions. So if someone tells you how many vertices you have, how do you choose a given map? You choose it proportional to the partition function of the statistical physics object you are looking at. Yes. So essentially, for example, if we are doing the Gaussian free field, if I have boundary conditions that are really different, then the Gaussian free field wouldn't want to connect these points, so it is more likely to do a graph that's not really that well connected. Okay. On the other hand, if all of the boundary values are the same, then it's more likely to have something which is where things can. Where different boundary values could be connected because it doesn't cost me that much. That's a little bit the idea. In another case, for example, if you have this is quite fun, imagine that you are at a really low temperature and you have a Ising model decorated object. And now you have certain patches of the boundary that are all plus, then all minus, then all plus, then all minus. Then essentially what the thing we want to do will be like a flower. We want to connect just the pluses together and just the minuses together, and all of the other things are not connected. And you get something like that. Okay? And this partition this one has a much better partition function than one where things could be connected, where we have many possible connections. Okay. So the third proposition, so here, and I will not show because I'm getting out of time, but also somehow I already gave you an idea of how to prove this type of things. So this satisfies both the weak and strong Markov property. So for the strong Markov property, the weak is essentially a right computation. The difficult thing is not when psi can take uncountably many values. So one has to take Radon-Nikodym derivatives and be a little bit wiser, but it's somehow straightforward. And for the strong Markov property, you need certain continuity. You need continuity on the boundary values, because what one does is yes. In this one it's quite direct. No, so one uses sorry, I'm thinking about the other one. In this one we use just the weak Markov property on the event. What am I missing something? For the strong Markov property one needs a filtration, but the filtration can be indexed again by the Qs. Yes, by the maps with holes. And what I have to look at the filtration is not only the maps with holes, but the maps with holes and the restriction of the decoration to the map with holes. So I have to look at all of that. And when I look at all of that, then what I have to put inside to finish my construction is just fill the holes with Boltzmann maps with the given boundary condition. So it is really nice because in this case one does not only have Markov property for the decoration when I'm fixing the domain, but I can forget the domain and discover the decoration and the domain at the same time, and still get a Markov property. And as one can imagine, there is also a uniqueness statement here. So the only ones that are the only reasonable ones that satisfy this property difference theorem, let can I fix it? Let Q and phi be a spin decorated map. Satisfying the Markov property. And we need that uniformly on B, the probability LB that Q has at least one internal vertex is positive. So we need that my graph at least can have one face. Okay, for this to work, then the following are equivalent. Q5 is a okay. So there is There is a parameter. Q is strictly positive now because I have one phase. There is a Q Boltzmann decorated, and 2 is that I am Boltzmann distributed when fixing the amount of vertices, and 3 is that I respect the shift. So if I so the only reasonable, I think that 3 is the reasonable one. So if I respect shifts and I have the Markov property, then there has to be a Q. Okay? Plus I respect the shift, and plus I am in the correct. Okay. Yes. And so let me give you an idea of the proof. So this one is much harder than the other one, but 2 implies 1 is not that hard. So again, we have to define a Q. Okay? So to define a Q, now it will depend on A, on B, on the map, and on the decoration of the map. And all of the work corresponds to saying that this Q doesn't depend on any of the parameters it is a priori depending, which will be the probability. So here, we got this one coming to itself, and then here, we have a map. And here, the probability of this one, but here I don't have to just put that one, I have to put the sorry. And I have to describe the decoration. Okay? So the decoration, this is the magic. So here I have edges. So here I have B0 as boundary condition. Yes? B0, B1. Yes? So the trick is choosing this vertex to have the same value of the spin as the decoration. So this can be easily done if we if our measure mu is a measure of discrete type of stuff, but it cannot be done when it doesn't. So one defines. Sorry, on time. Okay. So this is the right object to describe. Okay. Why? Because when one defines this probability, one has the probability of LB of having a type 1. Then now I have 3 B0s, so I have a probability L plus 1 B whatever star of a type 2, 0, L. But now I have exactly the same boundary condition as I had at the beginning. So the ratio does not depend neither on M nor on the decoration. And then one has to play with everything to at least see, okay, maybe that's what I can give you as a proof idea of how things work. So for 3 implies 2, I don't want to give you any proof idea, but I want to say you why you need, so this is why you need the probability of having at least one internal phase. And why? Is if you are measuring only trees, the condition of being spin decorated is not useful. So if someone gives you a tree, there is no way of using that you are spin decorated, because there are no spins you can put. Everything is already fixed. Okay? So that means that for trees, you have a measure P that has 2 parameters now. That satisfies the Markov property, but already with 1 parameter, you know that was characterizing your object. So the second parameter can make you any possible measure you want. So you have to have a way of making something that is not a tree to appear. At the points where you have a positive probability of getting something that is not a tree, you can somehow manage to understand trees. And that's a little bit tricky. So what you have to do is, the hardest thing is to prove that what you have, so 3 implies 2, it shows that if you respect the shift, then you are a Q Boltzmann distributed. Yes, and the main trick the main difficult part of doing that is to doing it for trees. And what you have to do is that you have to make a tree appear in something that it is not a tree. So you have certain peeling and then finishing up to you get a tree. And that's how you get the information out of trees. But if you just have trees, then the result in fact cannot be true because you have too many freedoms in L and B.
It's because the result fails, or
The result fails. The result fails because just with L you will have uniqueness. Mm-hmm. With L you have uniqueness. If you have B, you have too many values. So that means that it's not that you will have to have the same law. It's a little bit trickier. That if you just have L, so with B it's like you have a decoration. So you could get what any possible laws you want on trees, even they don't satisfy the Markov property when L is alone. But with L and B, somehow it's easier to satisfy the Markov property. So there are too many. Okay. So thirdly, I ran a little much more slower than I expected, even though I wanted to do it. But I just wanted to describe something surprising. The last 5 minutes. So what happens with? So now we would want. Okay. So why did we started doing this? It is because we wanted to understand level sets as a little bit what we discussed last time. So I want to start, I'm thinking about the Gaussian free field, and I want, or let's say, yeah, so here I'm thinking about the Gaussian free field, I start with boundary condition 0, and I want to arrive to boundary condition minus C, yes, in a Markovian way. So I can do this in a classic graph, using the metric graph, yes? So if I use the metric graph, I can start at 0 and stop the first time I hit minus C, and I can do that because the GFF on the metric graph is continuous. We would want to do the same thing on random geometry. Okay? So to do that on random geometry, one would want to define Boltzmann metric maps, not Boltzmann maps. So we would want to put length. And we would want them to have the Markov property. So a priori one would imagine that it's just like, okay, take a Boltzmann map and put random put exponential edges. Why? Because if you explore an exponential edge, well, the length that you have left to see is the same as that you had at the beginning. So that feels like that should be the natural way. And that is, of course, the right answer when you don't have decorations. But when you have decoration, this is not the right object. So let me quickly discuss about metric planar maps. So a decorated metric planar map will be a pair of this one. This is a metric map with different boundary length. Okay, so each edge comes, so it's like you sample a map and then you sample a length for each length. A priori you do not know what the law is. So what is the probability? Okay, so this is a decorated metric map. If the given your planar map, this phi tilde, this is a generalized Gaussian free field, or a generalized Ising model, meaning this is proportional to the product of V on the vertices of Q of certain measures. So always they have to have the same measure for every vertex of psi V, and then here you have product I running to J of this anomalized probability measure going from psi I to psi J of psi tilde restricted to I. Okay. So maybe I would have wanted to do a little bit more. Okay, so sorry, and I didn't put here what is the length. The length is the length of the edge. Length of ij, okay, in Q tilde, of course. So now I have this length, and what are the Boltzmann maps here? Well, the probability of a given pair in M tilde C tilde, this will be proportional. So this will be proportional to exactly. So here one has Q to the amount of vertices of M tilde times this energy product ij from psi I to psi j, psi tilde restricted to ij times exponential. So here I would want to say that I have exponential length. So I would put minus L times the length. So here length ij, length of ij. So you have this. So this is a Boltzmann map, so I'm already over my time, so I will just say 2 or 3 things about it. So the first one is that the lengths are not independent exponentials. They look like it. Conditionally on the object, conditionally on Q, on the graph structure, but not on the length, they are going to be independent. Okay. And conditionally on psi, there is something coming here. So here, the total mass of this is 1 over square root 2 pi L times exponential of minus, here I have I L I J. Yes. Psi I. Let's say this one. So even if I fix psi I and psi j, the lengths are going to be independent, but it's not going to be exponential. It's an exponential that is divided by this square root, and this has this minus L over ij here. So it is a really weird type of measure on the lengths. Okay? So if one wants to have the Markov property, together, one cannot just say, okay, I'm going to go through and it will not matter. I will just put exponential length. Why? It is because if you are taking values that are too different to your boundary condition, it is quite likely that you will continue growing, because you will not want to get together with a boundary condition that has two different values to you. However, if your values start approaching a boundary condition, then it is more likely that you will finish soon. So the Markov property to hide this an exponential is not good. You really have to take certain law regarding to this length. So this is one nice thing. So the other nice thing is one can build all the theory for this object. So one in particular, one has the weak and strong Markov property, as long as one needs essentially boundary continuity on the boundary condition, because one has to build the filtrations, and to go from the weak to strong Markov property, one has to be able to approximate from the outside and then take limit. So one needs to have a certain continuity, which one has here, and then these are the only measures on metric maps that are invariant under rerouting, and they have the Markov property. And the cool thing here is that we have a new type of peeling. So before, when we had a peeling, we took an edge, and we could either say, okay, we found a vertex, we found the edge was connected to myself, but I could actually just go and say that go a distance t and see still nothing. And this is a third type of peeling. And this is the one keeping every information. So it is like you go a little bit, and then you didn't find anything until time t, and you restart from there. Yes, so that's yes, mostly what I wanted to tell you, but just to
no, it was just something.
Yes. Yes, so thank you for staying
Yeah,
until
thanks for delivering this mini course.
Yeah.